All right, guys. In this video, we're just going to get started in some of the concepts in Unit 9. So, Unit 9 is one of those units where in chemistry, sometimes we get to it, sometimes we don't, sometimes we get to some of it. So this year we're kind of running out of time, so we're only going to focus on one little small portion on Unit 9. You're not going to have a Unit 9 test or anything like that, but a couple of questions on the final exam will go over or cover some of the content in this video today. So we're going to actually skip 9-1 because 9-1 is all about solutions. And we've already discussed a lot of things about solutions. So we know how to calculate molarity, and we know how to we know that like ionic solutions conduct electricity, covalent solutions don't, that kind of thing. So there are a few characteristics of water-based solutions that we already know about, but what we're going to focus on in this video and just for the last part of this year is 9-2, and we're not going to go through all of the acid-base chemistry theories. We're just going to focus on the most important one, the one that you do the most kind of calculations on and that kind of thing, and the one that most people, if you asked a random person on the street, what makes something an acid, what makes something a base, this is probably the theory that they would end up be discussing, even though they might not know the name of the theory. So we're just going to discuss the very surface of acid-base chemistry, and that's 9-2 in your visible learning document. But it's not. We're not in this video. We're not going to focus on all of 9-2. We're not going to focus on all the theories. Okay, so let's just jump into it. And a lot of the stuff will sound familiar because we have discussed acid-base chemistry when we first did nomenclature in Unit 4. Because you had to learn how to name acids and how to recognize if something was considered an acid. In stoichiometry in Unit 7, we did solution stoichiometry, and part of that was acid-base stoichiometry. We did an acid-base titration. And so we kind of have an idea of acid-base chemistry, and we just want to get a little bit better understanding of what's going on. All right? So let's go into that. All right, so again, technically there are three acid-base theories, and these are the names of them. You have the Arrhenius acid-base theory, the Bronsted-Lowry acid-base theory, and the Lewis acid-base theory. So what makes something an acid versus what makes something a base? Well, it depends on what theory you're talking about. So there is something called an acid in terms of an Arrhenius acid. There's something called an acid, but it's a Bronsted-Lowry acid. There's something called an acid, and it's a Lewis acid. There's certain things that act as all three sometimes, and the same thing with a base. There's an Arrhenius base, there's a Bronsted-Lowry base, there's a Lewis base. And again, you can have moments where in one reaction, a base is acting like an Arrhenius base, it's also acting like a Bronsted-Lowry base, it's also acting like a Lewis base. But we're only going to focus on Arrhenius theory. So the reason why we're only going to focus on this one is this is focused strictly on water-based solutions. So Arrhenius acid-base chemistry only happens in solutions where water is the solvent. Okay, and so what we have to start understanding is some characteristics about water, and what makes a water-based solution acidic versus what makes a water-based solution basic or neutral. Okay, that's really what we're going to focus on. Okay, so to understand Arrhenius theory, you must understand the nature of water. Okay, so coming into chemistry, if I asked, hey, what's the pH of water, everyone knows to say 7, and they know that 7 means neutral. Okay, but a lot of people don't really understand what pH is actually a measurement of, right? We know that less than 7 is acidic, we know greater than 7 is basic, and we know 7 is neutral. But like, what is pH a measurement of? Okay, so what pH is, it's a measurement of how much H plus is in your solution, hydrogen ions. Now, the real thing that's going on in water is you're getting what we call hydronium, H3O plus. But to simplify it, we'll call it H plus. The main thing you need to know is that hydronium and H plus, hydrogen ions or hydronium ions They are the same thing. They are synonymous in acid-base chemistry. They are the exact same thing. Okay? So if I say hydronium, I could replace that with H plus. If I say H plus, I could replace that with hydronium, whatever. Okay? It means the same thing. All right? But the lower the pH, the more hydronium or the more H plus you have in your solution. The higher the pH, the less, right? So we know a lower pH means acidic and a higher pH means basic, but really what's going on is the pH is a reflection of how much H plus you have. The more H plus you have, the more acidic the solution is, but that would mean the lower the pH, all right? The less H plus you have in your solution, the more basic it is, and that would mean you have a higher pH. So as the molarity of hydronium or H plus increases, the pH decreases. Okay. Now, so pure water has a pH of 7. Okay. And if I were to ask you this before you kind of looked over this sheet or before we've ever had a discussion on acid-base chemistry, if I asked you what's the concentration of H plus ions in your water, a lot of people would say 0 because it's pure water. Okay, but let's go and look at the equation for pH. So what this is saying is pH equals the negative logarithm. Okay, and it's log base 10 for those of you that know what that means. It's the negative logarithm of brackets H plus. Now remember, H plus and hydronium are synonymous, so another way to say the same thing is pH equals the negative log of hydronium ions. Okay, now what does that bracket mean? The bracket means the molarity of that something. So when you see something in brackets in a chemistry equation, it means the molarity. Okay, it's the concentration, and it's the concentration measured in moles per liter. So what this is telling us is if I want to calculate the pH of a solution, all I have to do is on my calculator hit negative log, and then whatever the molarity is of H plus or hydronium, same thing, whatever that molarity is, if I know what that is, the negative log of that number is going to be the pH. Okay, and so if you mess around with this equation a little bit, the higher this number gets here, the lower this number gets here. Okay, now, so let's think about it, right? The pH of pure water, you knew coming in was 7. So now let's take this equation and let's plug in 7 in for the pH value, and let's solve for the molarity of H plus. If we do that, this is how the equation would rearrange. So this is how you take this equation and rearrange it to isolate the molarity of H plus. And so that says the H plus molarity of a solution, or you could replace H plus with hydronium. The hydronium concentration of a solution is equal to 10 raised to the negative pH, the power of negative pH. So if your pH measurement is 7, 10 to the negative 7 is the molarity of your H plus. So what we just figured out is that in pure water, there's not 0 H plus, there's actually 1.0 times 10 to the negative 7 moles per liter of H plus. Okay, so it's not 0, but it's a really small amount, right? Pure water is mostly pure water. Some of it turns into H plus and OH minus, which we'll talk about here in a second. And the molarity of H plus in pure water is 1 times 10 to the negative 7. So if you take the negative log of this number here, that's 7. So that's why the pH in pure water, and really it's only at 25 degrees Celsius, but let's just assume we're always there, it equals 7. Okay, the pH of pure water is 7. Okay, so the question is, where is the H plus coming from? And the H plus is coming from what we call the autoionization of water. Okay, and there's 2 ways to go about it, and this might kind of show you where we say hydrogen ion or hydronium ion. So one way to think of water is that water, kind of like an ionic compound, some of the water molecules can dissociate, and you can think of water as H plus and OH minus. Okay, so some water molecules will break up into H plus ions and OH minus ions. Okay, now what's really going on is the water molecules are bumping into each other, and sometimes one water molecule can take an H plus away from another water molecule. And when that happens, if this water molecule gains an H plus, it becomes H3O plus, hydronium, and the water molecule that lost an H plus becomes hydroxide. Okay, but either way, we got water yields H plus and OH minus, or we have water yields H3O plus plus OH minus, and that's why H plus and hydronium are synonymous. Okay, but what we want to take from this is, yeah, not only does pure water do this to produce H plus, but notice for every one H plus that's produced, you get one OH minus. So not only is there 1 times 10 to the negative 7 moles per liter of H plus in pure water, that would mean there's 1 times 10 to the negative 7 moles per liter of hydroxide in pure water. Okay? So really, something's neutral when the amount of H plus and the amount of OH minus are equal to each other. Okay? So when the amount of H plus and the amount of OH minus are the same amount in a water-based solution, you will have a neutral pH. Okay? But now we kind of enter in, well, okay, so if water has H plus in it, but it also has OH minus, we have another measurement of acidity or basicity, how alkaline the solution is, how basic it is. All right, and that's the pOH scale. Okay, so pOH scale is just this, is basically the same as the pH scale. It's just flipped around 7. 7 is neutral, but a low pOH would be basic and a high pOH would be acidic. It's kind of flipped around 7. Okay, well, how do you calculate the pOH? Well, the pOH is just the negative log of the molarity of hydroxide. So if you know the molarity of hydroxide, you could take the negative log of that, and that'll give you the pOH measurement. Here's the deal, okay? Every solution has both a pH and a pOH measurement. Every single water-based solution. An acid has a pH measurement and a pOH measurement. A base has a pOH measurement and a pH measurement. Every single water-based solution, whether it's acidic, basic, or neutral, can have a measurement of pH, and it will also have a measurement of pOH, because in every single water-based solution there is an amount of H plus and there is an amount of OH minus. Okay, if it's pure water or if it's neutral, the amount of H plus and OH minus is the same. 1 times 10 to the negative 7 moles per liter for the H plus, 1 times 10 to the negative 7 moles per liter for the OH minus. Okay, now here's the deal. If you take the negative log of the H plus and get the pH, and you take the negative log of the OH minus and get the pOH, the sum of those two measurements will always equal 14. So if you think of pure water, it has a pH of 7 and it has a pOH of 7. 7 plus 7 equals 14. Okay? But this will always be the case. So let's say you have an acidic solution that has a pH of 6. All right, it's not very acidic, 6 is just a little bit less than 7. So a pH of 6 would mean you also have a pOH of 8. The pH is 6, the pOH is 8. 6 plus 8 adds up to 14. So in that case, if your pH is 6, your molarity of H plus would be 1 times 10 to the negative 6, and your pOH would be 8, so your molarity of OH minus would be 1 times 10 to the negative 8. Okay? So every water-based solution, no matter what you put in water, as long as it makes a solution with it, it dissolves in it, it mixes well with it, okay? As long as you do that, okay? Okay, so in every water-based solution, no matter what you put in it, no matter what, if it's an acid or a base or it's something that makes the solution neutral, the solution itself will always have a pH and a pOH value. And that pH value and that pOH value always have to add up to 14. Okay? All right, so now let's really talk about what Arrhenius acid is. Okay, and Arrhenius acid is something that when you add to water, it makes the solution acidic, so it gives it a pH less than 7. But at the same time, it's going to make the pOH of that solution greater than 7. Okay, so what's really going on is that Arrhenius acid is something that when you add to water, it increases the concentration of H+, increases it above 1 times 10 to the negative 7. So what I want you to think is this molarity, 1 times 10 to the negative 7 moles per liter, is your starting point of every water-based solution. It's your starting point for how much H plus you have, and it's your starting point for how much OH minus you have. And as one of those increases above that number, the other has to decrease below that number. So an Arrhenius acid is something that when you add to water, makes the H plus concentration go above this number, 1 times 10 to the negative 7. But at the same time, it's making the OH concentration go below that number. So what it's doing is it's making the pH go down and making the pOH go up. It's increasing the amount of H plus in the water, and at the same time, it's decreasing the amount of hydroxide. So a base does the opposite. A base is something that when you add it to pure water, increases the concentration of hydroxide, and at the same time decreases the concentration of H plus. So really simplistic, something that produces H plus in water is an acid. So you want to think H plus, that's acid. Something that produces OH minus in water is a base. OH minus is base. And what do acid and base do to each other? So when OH minus comes in contact with H plus, they neutralize each other and form HOH, which is H2O. Okay? So why do we consider these solutions acidic? Okay, why is HCl an acid? Why is HBr an acid? Why is H2SO4 an acid? Well, when you put them in water, they dissociate and form H plus. Okay? Or when you show it react with water, the water takes the H plus away from that and produces hydronium. Remember, this and this are the same. So something that produces H plus in water is the same thing as something that produces hydronium in water. This is kind of the more complicated way to think about it, and this is the more simplistic way to think about it. But it's not because chloride's in solution, it's because when I add this to water, I get H plus. That's what makes it an acid. So that's why, like in Unit 4, when we first bring up, like, how do you recognize an acid? It's H in front. H in front, and when you add it to water, it can dissociate, just like an ionic compound dissociates, and one of the ions it dissociates into is H plus. Well, if that's the case, then you're going to have an acid, because you're going to increase the amount of H plus. But what's going on in the background, the thing that we're not focused on here, is as this concentration goes up, H plus, the OH minus concentration has to come down, because the pH and the pOH of the solution always has to equal 14. Okay? So why are these salts, when dissolved in water, why are they basic? Okay, well, they're basic because look at what their anion is, hydroxide. So when this solid salt dissolves and dissociates and forms aqueous ions, one of those aqueous ions is hydroxide. So when I add sodium hydroxide to water, I get hydroxide. That's why sodium hydroxide is considered a base, because it produces hydroxide in water. Okay? But then you have other things that can be basic, but then if you look at the formula, you're like, well, where is the OH minus coming from, right? So ammonia is a weak base, but it's a base, okay? And so if you look at ammonia, NH3, and you're like, well, wait a minute, there's no hydroxide, there's no OH minus. If you don't see OH minus in the compound that you're calling a base, that means the OH minus is coming from the water. So where's the OH minus coming from? Well, the ammonia bumps into a water molecule. It takes an H plus away from the water molecule. That's where ammonium comes from. And then if water loses an H plus, you get OH minus. So adding this to water produces hydroxide. That's the definition of an Arrhenius base. When I add this to water and I get hydronium, that's the definition of an Arrhenius acid. Okay? All right, so the main things to remember are your acid-base equations, okay, and that H plus and hydronium are the same thing. So anytime you see H plus, you could replace it with hydronium, or anytime you see hydronium, you could replace it with H plus. It's the same thing. But if you don't understand logarithms, then make sure you know the pH equation this way, but make sure you know it this way too, because if I give you the pH, all you have to do is 10 raised to the negative pH will give you the molarity of H plus. Okay, and this is how you find the pOH. You need the molarity of hydroxide. But if you know the pOH, you can do 10 raised to the negative pOH, and that would give you your molarity of hydroxide. And then this is the thing that ties the solutions together. The pH plus the pOH always has to equal 14. So if you can figure out a way to get the pOH, you can subtract that from 14 to get the pH, and then you could do 10 to the negative pH to get the molarity of H plus. Okay, so really, if you know the molarity of H plus, or you know the molarity of hydroxide, or you know the pH of a solution, or you know the pOH of a solution. If you know one of those four values, you can calculate the other three just by using these equations. Okay, pretty simple. All right. So again, that's just a quick intro to Arrhenius acid-base theory. The next one that comes out is Bronsted-Lowry, and Bronsted-Lowry and Arrhenius are very similar, but slight differences. So the only thing you have to worry about is, hey, if I give you hydroxide, be able to find the pH or the pOH. If I give you the molarity of hydronium, be able to find the pH or the pOH. Or if I give you the pOH, maybe be able to figure out the molarity of hydroxide, but also maybe be able to figure out the molarity of hydronium. And if I give you the pH, be able to figure out the molarity of hydroxide. Okay? So you're just using those equations. Okay? So once you read these notes and you've watched the video, go and answer that Schoology assessment on 9-2, and you should be, if you can answer those questions, then that's all you need to know for acid-base theory for this year. Okay, if you take AP chemistry later on, we have a whole unit on acid-base chemistry, so we'll spend a lot of time on it. All right, so have a good one.